So today's notes, we're going to cover section 5.7, which is about systems of linear inequalities, and our goal will be able to write and graph them. So what we're going to do is just rely on what we already know. So in sections 5.1 to sections 5.4, which we also had a quiz on, we studied systems of linear equations, right? So systems of equations, like I have one over here that you'll need to add to your notes. Like this is a system because there's two equations that we're trying to solve at once. In this section, we're doing systems of inequalities. So there's a lot of similarities that we'll go over to help us. So just to remind us, when we were solving a system of linear equations by graphing, what we had to do was just graph each of the lines and see where they touched. So like this first one here, which I'll do in blue, has a y-intercept of 2, and we can see that the slope was 1. So we make a border, or sorry, we make a line here, and then we would just connect the dots, and then we move on to our next equation, which is y equals 2x minus 1, and it has a slope of 2. We can see after I plot these two, I'm just going to plot a few more here. I would ask that you're doing the same. So I just place the y-intercept of -1, and we use the slope of 2. So when we connect these, we can see that they touch right there. Now I'm going to actually highlight that in brown, just alluding to later brown, or maybe even black. But that's where they touch. Now, when we're doing a system of inequalities, we're going to essentially do the same thing. We're going to graph each inequality rather than graphing each line, and we're going to see where do they intersect. Now, two lines will intersect at a point, but we'll notice when we do our inequalities, we're going to ask ourselves, where do the shaded regions intersect? So just as a nice reminder, where do the lines intersect is how we did it before. What we're going to be looking at with a system is where do the shading intersect. In section 5.6, we went over how to create a linear inequality. So like we have a system, we just need to do them both. So I do this one first in blue. So we're going to plot the border, and we know it has a slope of 1. Now when we're doing inequalities, we know that the borders, or in other words, the lines that we connect them with, have to either be solid or dashed. So with this one, because there's no equal to, we are going to put a dashed border. Now after the border, when we do inequalities, we also need to determine which side to shade. So I'm going to test the point 0, 0 to help me determine what side to shade. So if I test 0, 0 in the original inequality, is 0 less than 0 plus 2? So is 0 less than 2? So that is true. So if 0, 0 is a solution, that means I want to shade everything on that side. So I'm going to shade everything below this line. Now I happen to have highlighters, so I'm going to use those. And I'll show you what to do in the next example. If you don't have highlighters, we can just go ahead and shade with your pencil. So just like we did over here, we plotted the first line, and we move on to the second line. So just what we're doing here, we plotted the first inequality, so now we should plot the second inequality. So this one has a y-intercept of -1. Now what we're doing here is we're just plotting them on the same coordinate graph, just like the other one wasn't there. Similar to what we did over here. We just plotted two lines on the same graph. So we're going to make this second inequality. So the slope is 2. So we go up 1 over 2, up 1 over 2, up 1 over 2. I'm going to do that in both directions so I can make the border use my entire graph. Now here, there is an equal to, right? That little equal to part there helps me know that I'm going to connect these with a solid line. The same thing, once we do the border, we have to test what side to shade. So with this one, I'm also going to test 0, 0 because it's not on the red line. So if I tested 0, 0, is 0 greater than or equal to 2 times 0 minus 1? Is 0 greater than -1? And that's true. So I would also shade that side that contains 0, 0. So 0, 0 is above the red line. So that means I'm going to shade above the red line. Everywhere I can see, I'm going to shade above the red line. Now, just like we did with equations, we wanted to say, well, where did they intersect? But with inequalities, we want to know where does the shading intersect? So since I have colors here, we can see where does the blue shading overlap the red shading? Well, that is right here. So I'm going to come back and make my final solution region nice and apparent. So I'm always going to say, let's make that as dark as we can so we can label these the solution regions. So I'm just going to write that in words too. These are the solutions. The solutions are shaded both colors because they make both inequalities true. So that brings us to our next part. Like after we make the graph, whether we see where two lines intersect or whether we see where two shadings intersect, we always want to determine if something is a solution. So like when we did equations, we know that if an ordered pair was a solution, we just had to plug it in to the original equation. And here's just the definition from the textbook. So if it wants us to check if 3, 5 is the actual solution to this inequality, right? Because we think they intersect at the point 3, 5. So if it is a solution, it should make both inequalities true. So we'd test the first one. So instead of y equals x plus 2, we'd plug in 5 and 3 for x and y, and we'd see that it makes the first inequality true. But if it's a solution to the system, it has to make both of them true. So it also needs to make the second one true. So the second one is y is equal to 2x minus 1. So if I plug in y and I plug in x, I should see that it makes both equations true. So this is a solution because it satisfies all the originals. And I just abbreviated because. Now, with systems of inequalities, the same exact thing is true. So over here, again, they do want us to test, is this point a solution, is this point a solution, and is this point a solution? So if they are solutions, they make both of the original inequalities true. So 3, 5, we'll test that right here. So we'll plug it into the first one. So the first one is y is greater than x plus 2. I'm just going to copy the other original right away. The other original is y. Oops, sorry, I have my symbol wrong. It's a less than. And then the other one is y is greater than 2x minus 1. Greater than or equal to. So if I tried 3, 5, 3, 5 should make both of them true. So if I plugged in 5, is 5 less than 5? Well, no, that's not true. 5 is not less than 5, so it's not a solution. So this one is not a solution because it doesn't satisfy all of them. And we can go see that up here in the original too. This point right here, 3, 5, is not on both lines, right? The blue line is not shaded in because it's an open line. We would call it dash, so it's not shaded in for both of them. So we should see it's not a solution. If we check something like 0, 1, so if I plug 0, 1 into that one, is 1 less than 0 plus 2? Well, yeah, 1 is less than 2. And it also would make this one true. We'd have to check, is 1 greater than or equal to 2 times 0 minus 1. So is 1 greater than or equal to negative 1? Yeah. So this one is a solution because it makes both of them true. And we can also see that the point 0, 1 is shaded in both colors. And we can see for that final one, 2, 2. If we found that on the graph, 2, 2 is right here. It is not shaded in both colors. Now what I'm going to also have us see is that it's shaded in blue. So if I plugged it into the blue one, right, if I looked at 2, 2, if I plugged it into the blue one, it was shaded in for the blue one. So it should make the blue one true. But we noticed that it wasn't shaded in red, right? So if it's not shaded in red, it should not make the red one true. So if I tried the red one, and I plugged in the x and the y, so plugging in x and then plugging in y, I would see that it is not true for this one. 2 is not greater than 3. So checking solutions, they just need to make all the original inequalities true. The last part of the notes for today, I want to do one more example and then work into some special scenarios. So let's just do summarizing that. If you were graphing a system of inequalities, you have to determine the solutions. And this is what a problem would look like on an assessment or your homework. So what we need to do is we need to graph both inequalities. So we'd graph this one here first. Now with this one, when we're doing inequalities, it's okay to use the x-intercepts and the y-intercepts because we just need to create that border. So for the x-intercept, I can let y equal 0. And here I don't care about the less than or equal to. I just want to know what the x-intercept is. So the x-intercept is negative 2. And if I did the y-intercept, I would let x equal 0. Again, I don't care about greater than or equal to for the intercepts. So I'm just going to make it an equal. So we can see the x-intercepts are negative 2, and the y-intercept is positive 4. So I put a dot at negative 2, the y-intercept at 4, and I look at the original inequality symbol. There's no equal to, so this is a dashed line. Now I need to determine where to shade, so I'm going to test a point that's not on the line. So I'm going to test the point 0, 0. So 0, 0 is below the line. Now here, I'm going to show you what you would be doing is if you didn't have all these extra colors. So I'm going to start to do this all just in black. So just like you would be doing at home. What if I don't have highlighters? How can I show my work? How can I see the overlap of the regions? So if I tested 0, 0, if I plugged it in, -2 times 0 plus 0 needs to be less than 4. And 0 plus 0 is less than 4, so that works. So there's two strategies. So the first one I would say is using up and down shading versus left and right shading. So here I shaded below that line. So I move on to my next border line. So my next border line is 2x plus y is greater than 4. So in red, I'm just going to find the x-intercepts and the y-intercept just so we know where they came from. So for the x-intercept, if y was 0, we have 2x plus 0 is equal to 4. So x is 2. If I was finding the y-intercept, we'd let x equal 0. So we see again that they actually have the same y-intercept of 0, 4. So I'd plot those 2 points. So here's 2, 0. Now I'm going to go back to black. So here's 2, 0. And here's 0, 4. And because these also do not have an equal to, I'm going to connect them with a dashed line. Now with this one, I need to choose a point. So I'm going to test a point that's not on that dotted line. And 0, 0 is not on that dotted line, so I can actually test that again. So if I tested 0, 0, is 2 times 0 plus 0 greater than 4. So is 0 plus 0 greater than 4? And that's a no. So I'm going to shade the side that doesn't have 0, 0. So for the line that I'm working with, which I'm just going to highlight, this line here, 0, 0 was below the line. So I need to shade on the other side because 0, 0 didn't work. Now here I'm going to use horizontal shading. So I would shade on the other side of the line. So I'm using horizontal shading of that line. So for the final solution region, I'm just asking where do I have vertical and where do I have horizontal shading? So when you're doing your final solution region, I'm just going to put this as a little note on the notes, and you need to write this down just as a verification that you took the notes, is always make your final solution region easily visible. So what I would recommend that you do is go back and shade it like super dark, or if you have a different color, do a different color. But I can see all these places right here. This is where I had horizontal and vertical shading. So that's my solution region to that system of equations. So any point in here, any xy pair is a solution. In the next example, I'll give you another strategy. If you don't like the horizontal and the vertical shading, what's another method I could use? So the last part of the notes for today is just looking at special cases. When we did system of equations, we were expecting a system of equation to have one solution. That's kind of what we were expecting. So if it wasn't one solution, there could have been some special cases, like there could have been no solutions because our lines never touched, or there could be infinite solutions because the lines were the same. The really only special case that we want to worry about with inequalities that would be special would be that there are no answers, because by definition, inequalities always have an infinite number of solutions. Like for example, if I said what numbers are less than 3, well, there's an infinite number of those. So because inequalities usually have an infinite number of solutions, the only special case that we would have here is when there's no solutions. And what we saw with equations is that with equations, there was no solutions if the lines never touched. So with inequalities, there will be no solutions if the shaded regions never touch. So do a quick example of those. So here we need to graph each system and then determine the solution region. So the first one, and here again, I'll show you another method if you don't have colors. So we'd have to graph this first line. So I'm just going to put a little number 1 next to it so I know I'm working with the first line. So we just find the x-intercepts and the y-intercepts with this one. It works out pretty nice. So the x-intercept, and again, when I'm working with intercepts, I don't really care about greater than or anything. So I just make it an equal to. So we can see our x-intercept is 2. If we look for our y-intercept, we'd have 0 minus y is equal to 2. So we'd get y is actually equal to -2. So we can go plot those points. So 2, 0, 2, 2, 0, and 0, negative 2. And we're going to connect them with a dotted line because that symbol doesn't have an equal to under it. So we'll connect it with a dotted line. Now I need to test aside to shade. Now I'm going to test 0, 0 again. So if I test 0, 0 in the first equation, is 0 minus 0 greater than 2? Or in other words, is 0 greater than 2? And that's a no. So another method that you can use to show your shading. So 0, 0 was not a solution. So 0, 0 was above the line, which means that I would have to shade the other side of 0, 0, which is below the line. So you can put in little arrows and say, okay, I would have shaded below this line. And then, or maybe even want to write the word below. I'm going to shade below that line. I do the same thing with the next inequalities. I'd have to go make the border and graph that one. So x minus y is less than or equal to negative 3. That's just our second equation, so I know where my work is coming from. So if I plug, or if we made the border here, we'd use our x-intercept. So I could do like x minus 0 is equal to negative 3. So our x-intercept is at negative 3. If I found the y-intercept by letting x equal 0, I would see that the y-intercept is negative 3. So again, we can go graph those. They actually have the same x and y-intercept. So negative 3, and then negative 3. Sorry, I just made a small mistake. Sorry, this is a negative and that's a negative. So this is actually positive 3. I'm sorry about that. The y-intercept is a positive 3. So then when I connect those, again, I'm going to look at the symbol. This does have an equal to, so I'm going to use a solid line. So when I connect these with a solid line, and I need to test a side. So I am going to test 0, 0 again. So if I were to test 0, 0, is 0 minus 0 less than or equal to negative 3? Is 0 less than or equal to negative 3? And that's a no. So that means I would not shade the side with 0, 0. I'd have to shade not this side, but I'd shade the other side, which is above that line. And I could actually write the word above. So here I'm asking, where am I shading below this line and above that line? Well, there is no area that's going to happen. So this is our example of no solutions. Now, if I go back and put in the shading, if I did have colors, I would have shaded above this red line. So this is our red border. I would have shaded above that. Our blue border was right here. We would have shaded below that. What I would like us to see here as well, just connecting to our other things, these are parallel lines, right? The slope of this one was up 1, 2, 3, and over 3. So the slope of this line was 1. The slope of this line was up 2 and over 2, so the slope of this line was also 1. So we know that they're parallel lines, so their shading would never intersect.